In the previous video, we saw how we can derive the posterior given a beta prior and a binomial likelihood. Now let's look at some example datasets and example priors and their combinations and see how the posterior looks in these settings. So just as a reminder, we have the prior, which is beta of beta h and beta t. Beta h and beta t are parameters of the beta distribution. And we have data that we have collected, and that amounts to alpha h number of heads and alpha t number of tails. And we have derived the posterior distribution, which is P of theta given D. So D is data. Theta is the parameter of the coin that we want to estimate. And now we derive this to be from a beta distribution with parameter values beta h plus alpha h, beta t plus alpha t. Now let's again repeat what these different values are. Alpha h is number of heads. Alpha t is number of tails. Beta h and beta t, parameters of the beta distribution. So we saw that beta h adds to alpha h to form one parameter value, and beta t adds to alpha t to form another parameter value of the beta distribution, from which we are going to sample the posterior distribution. Okay, now for our example in hand, we have data sets with 4, 20, and 200 examples. And each data set has exactly half heads and half tails, which means without the posterior distribution, if we were to use maximum likelihood, what would be the estimated values? It would be number of heads by number of heads plus number of tails. Since there are half heads and half tails, we will get our parameter value to be 0.5 if we use MLE. Right? Now, suppose we have two different beta distributions here. One is beta 2.1, 1.1, where beta h value is 2.1, beta t value is 1.1. Another beta distribution where we have beta h value 20 and beta t value 10. So we want to see how these two prior distributions affect this data set. So we know that by just using maximum likelihood, our parameter estimation value is 0.5. So now we are going to see how these priors are going to affect this value and which of these priors would have a greater effect on this value. Okay, so let's first look at the first data set, 4 examples. This is just the priors. These two are just the priors. And this in the bottom 2 graphs are the posteriors. Okay, we saw that if the A value or the beta H value is greater than beta T, the curve shifts to the right, and the peak of the curve occurs more towards the right if beta h is greater than beta t. So in both these priors, we see that beta h is greater than beta t, so the curve shifts to the right. But we see that the curve is way more prominent in the first one, where beta h value is 2.1, beta t is 1.1. That is because there are only in all 3.2 worth of value here, but while here we have total of 30. So we can see that the number of samples for this beta, the first beta, is very small, which means this has a lesser of this peak which we see in the right curve. We have more data points, so the curve is more prominent and the peak is way more pronounced in the right. So just to give you an intuition of how the values would translate into the form that you see in the graph. And for the posteriors, so we see that we have beta of 4.1, 3.1 after adding alpha h and alpha t. So alpha h is equal to 2, alpha t is equal to 2. So that means that we have beta of 2.1 plus 2, right, 1.1 plus 2. So which gives us 4.1, 3.1. Now we can see clearly that between 4.1 and 3.1 there is just difference of 1, and it's almost equal. So that, which is why our graph is now moving towards 0.5. Remember that if they are both equal, the peak would occur at 0.5. It would be a symmetrical curve. Now it's not exactly equal. One is slightly more than the other, which in this case beta h, or the a value of the beta distribution. So this one is greater than 3.1. So which means that the curve is going to shift, the peak of the curve is going to occur little after 0.5 towards 1, but little closer to 0.5 here because the values are sort of equal, almost equal. So that's why we have the curve shifted towards 0.5 and the peak occurring a little after 0.5. Now let's look at the other example. So here we have a stronger prior because the values are higher. And if you can see here that alpha h value and alpha t value are not going to change for both these examples. Alpha h is 2, alpha t is also equal to 2. Now when we add this to the new beta h and beta t values, we get 20 plus 2, 22, 10 plus 2, 12. Now the difference between these two values is 10, which is way more than the difference that we got between the values 4.1 and 3.1. While the difference was 1 earlier, now it's 10, which means that this is going to make the shift more prominent, shift from 0.5 way more prominent because a value of 20 is getting added to 2, and you can see that the prior has way more prominence in the right graph here, dominated by the prior. This graph is dominated by the prior because the values 22 is very close to 20, 12 is very close to 10, and the difference 10 is maintained here. So it's very the posterior is dominated by the prior here. Whereas in the first one, it is dominated by the data, because the data is almost the same value as the beta h value. Another thing that you need to understand here is that as the value for the parameters increases, the curve becomes narrower. There's more and more certainty around the curve, and it becomes narrower and narrower, and you can see that here this one is narrow, whereas this one is wide. And that is because of the values, the parameter values here. If they are higher, it just becomes narrower. So if they are higher and not equal, then it becomes narrower, and your value of estimation goes further away from 0.5, though the data clearly here suggests that it's close to 0.5. The prior plays a very important role, and it's further away from 0.5 when the prior is stronger. So which of these two priors is a stronger prior? Because the values are higher, the parameter values, this is a stronger prior than this. All right, let's see another example so we can understand this better. Now we have 20 examples. So now we have more examples. And with more and more examples, the prominence of your prior in the posterior equation should come down. So let's see if that is happening. So now we have more examples, and we have 10 of each. So we have here, this is the prior again, and this is the posterior. So now we have alpha h equal to 10, alpha t equal to 10, and we have beta of 10 plus 2.1, comma 10 plus 1.1. So then we have beta of 12.1, comma 11.1. So now we can see that these are high and the difference is smaller. So the curve should be very close to 0.5, closer to 0.5. So now in this setting, now let's evaluate this by the same metrics that we had before. So is this going to be narrower? Yes, because the values are higher. Is this going to be ruled by, is this posterior going to be ruled by the prior or the data value? The prior value is 2.1 and the likelihood value is 10. So clearly alpha h is greater than beta h. Alpha t is also greater than beta t, and their summation is the new parameter value, and hence the contribution of alpha h here is greater than that of beta h, and we can say that for this posterior, the likelihood function or your data contributes more. So here clearly data contributes more to the posterior. Now let's look at the other example and ignore these values. These values are wrong. and the curve will be close to 0.5, and I think there's a mistake there as well. So the curve will be close to 0.5. So remember all those things that we discussed and went through. I think the curve itself may have a mistake, and I will try to correct that. Okay, and let's look at another example. Here we have beta 2010, and again we want to add 10 to it, right? Alpha h equal to 10, alpha t equal to 10, and beta of 10 plus 20, comma 10 plus 10. So here again we can see that still the prior contributes significantly to the posterior. And the difference between these two values is still great, pretty great. And since the value is higher, the curve also becomes narrower. So the curve becomes narrower, but still the contribution of the prior, which is coming from these values, is pretty high. It's actually greater than alpha h value in one case, and it's equal to alpha t value in the other parameter value. So it's still contributing pretty much a lot, and hence it's going to be narrower, and it's also going to be away from 0.5 because the first value is greater than the second value, parameter value. It's more towards 1, it's away from 0.5. So this is going to give us an estimate of greater than 0.5. And which of these, between these two, which is closer to 0.5? This one is closer to 0.5. Closer to 0.5. And because the data contributes more in this one when compared to the other one. Now let's look at the last example. Here we have the same priors, but now we have 100 examples. So 100 is definitely a high number for both of these priors because the highest parameter value for in the priors is 20, and 100 is 5 times that. So it's still orders of magnitude higher than this parameter value, and hence we can see that both these graphs, both for the posterior, look kind of similar, except for a little bit of narrowness and shape. They are going over 0.5, very close to 0.5, and the significance of the prior has now decreased in both these posteriors. So again, just so we are clear, this is the prior and this is the posterior. And alpha h is equal to 100, alpha t equal to 100, and now we have beta of 100 plus 2.1, comma 100 plus 1.1, which is equal to beta of 100 then 2.1 and 101.1. Here we have alpha h equal to 100 again, alpha t equal to 100, beta of 100 plus 20, 100 plus 10, beta of 120. Now we can see that 102 and 101, these two values, these are closer. So this is more going to curve more around 0.5 than around this, because as close as the values, if the values are closer, then the curve is going to be symmetrical. So this is definitely going to be way more symmetrical, closer to symmetrical, and then this is still going to be closer to 0.5, the estimation value, than this one, this other one on the right. But here again, but the difference has diminished. You can see clearly that the difference has diminished, and the effect of the prior is sort of overruled by the effect of the data points, because now we have 120 is to 110, and 100 of that is coming from the data points. So this is definitely driven more by data now. And this is less closer to 0.5 than this other one, but still it would be closer than the previous one where we had 20 examples. So it's closer than that one, but it's definitely is losing to this other one. So we have, that's why we have concept of a stronger prior. A stronger prior can overrule data and can have more effect on the posterior than a weaker prior. But even a stronger prior can be completely ignored if we have more and more data. Suppose we had 200 examples here. Suppose we have 2,000 examples. Then the contribution of this prior is not going to matter in a data set of 2,000. And 20,000 will diminish even further, and so on. So it would no longer be a strong prior if we have 20,000 data points. But it still has some effect on 100 data points, because there is a difference here which is noticeable.